All right, welcome back to Speech Understanding. I'm in the terminal now. Let me go to KCGI Intro Speech Understanding. And let's see, we have here lectures 1 through 6 for the last 6 lectures. So let's fetch the new release. As you know, we should type git fetch release, and that will download the code. We can see that we've downloaded it, but it hasn't been merged yet. And so in order to merge it, we need to type git merge release slash and then dash M followed by any comment. Let's say merging lecture 7, and then dash allow unrelated histories. That should merge everything. Now, if we list, we can see that lecture 7 exists, so we can change directories to lecture 7. In lecture 7, we see that there's a grade.py, a homework7.py, and a lecture 7 notebook. Since there's a notebook here, let's go ahead and open it. All right, last time you may remember we learned about sound. We learned how sound is stored on a computer. We learned that sound is stored by storing its individual samples. Individual samples of a sound waveform are stored with a certain number of samples per second, typically 8,000 or 16,000 or 48,000 or 44,000. And we learned in particular about cosines and sine waves. We learned that a tone, a pure musical sound on the piano is a sine wave at a particular frequency, and that the frequency of the middle A on the piano is 440 hertz. The frequency of middle C is around 256 hertz. Today, we're going to look at how do we decompose a complex sound into several component sounds. So in particular, I'm going to talk about musical chords. And musical chords will allow me to talk about the discrete cosine transform and the discrete Fourier transform. But before I talk about musical chords, let me introduce the background that's necessary to understand the discrete Fourier transform. That background is something called the orthogonality principle. And it's named after, if we go to Wikipedia, I think we can look up what orthogonality is. Orthogonality just means right angles. So the line AB is orthogonal to the line CD. They're at right angles to one another. And what that means is that if you shine a light down on AB, the projection onto line C and D has zero length. Right? So orthogonal means that if you go in the direction from B toward A, you make no progress at all toward D. It means that the relationship between these two lines is zero. And so this idea of zero relationship is something that we're going to use for pure tones. You remember that in audio, everything is a pure sine wave or a pure cosine wave. And cosines and sines have this interesting property that when you multiply them together and average, the average is zero. So the way I've stated it here, the orthogonality principle is that the average value of the product of two pure tones with different frequencies is zero. So we're going to take a cosine that has 3 complete periods, and a cosine that has 4 complete periods. If we multiply them together and add the result is zero. Take one that has 3 complete periods, a cosine that has 4 complete periods, so frequency of 3 and frequency of 4, over, let's say, 20 consecutive samples. Oh, in the text I say 24, so let's make it 24 complete samples. And let's calculate, we'll make a small n axis, which is the integer range from 1 to capital N. Let me just convert it to a NumPy array. The numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and 23. In other words, I'm just going to explicitly create a sample array, small n, that goes between 0 and capital N minus 1. And then over that entire range, I'm going to calculate the cosine. X will be the cosine at frequency k, and y will be the cosine at frequency m, right? So 3 hertz and 4 hertz. And then I'm going to print out the total of the product between x and y. And then just for information, I'll plot first in subfig 0, I'll plot x. Second in subfig 1, I'll plot y. And third in subfig 2, I'll plot the product of the two of them. So now I have um, it says that I can't create an array that's that large. Well, let me go ahead and just um, create the range up to size capital N then. All right. So I have the small n axis goes from 0 to 23, as you see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. And on the top here, I have the cosine at 3 hertz. So it has 3 complete cycles. In the middle, I have the cosine at 4 hertz. So it has 4 complete cycles. And at the bottom, I have the product of those two cosines. So you see this one is positive 1 times positive 1 is positive 1. Positive 3/4 times positive 1/2 is positive 3/8. When one of them is 0, their product is 0. When both of them are negative, their product is positive. Again, here, both of them are negative, so their product is positive. Here, one of them is negative and one of them is positive, and so the product is negative. And what you can kind of see is over this entire period, 3 periods and one of the cosine, 3 periods of x and 4 periods of y, there are roughly as many positive samples as there are negative samples, right? The positive part here equals the negative part. And so when I add them all together, the total is 10 to the minus 15th. The total is basically 0. Right? The average value of this bottom plot is 0. And so as I've shown in the equation, when I multiply the cosine of 3 hertz times the cosine of 4 hertz and take the average value of that product is 0. And this is called orthogonality. This is just like the fact that if you shine a light down over the AB line segment, the shadow on the CD line segment has 0 length, right? The dot product between these two lines is 0. There's no connection between them. In the same way, there's no connection between the 3 hertz cosine and the 4 hertz cosine. They have a 0 average. So this is called orthogonality. This is the same as saying that this x is one line, y is another line, and those two lines are perpendicular. That's interesting primarily because it has exactly one exception. And that one exception is when k is equal to m. If both x and y are at the same frequency, if k is 3 and m is 3, then when I multiply x times y, that's the same thing as taking x squared. And x squared is always positive. And so the average of something that's always positive has to be positive. Here I have 20 consecutive samples. And over these 20, let's make it 24. Let me make it 24 consecutive samples. And I'll take 3 complete periods. So here's 3 complete periods. Here's another cosine at 3 complete periods. When I multiply them together, the result is always positive because these two things are always the same. When x is negative, y is also negative, and so it's always positive. And in fact, if I average it out, I have 24 samples here. When I add up these 24 samples, half of them are plus 1, half of them are 0. So the average value is 24 times 6. Let me actually calculate the average. Let's take the average of x and y, and I'll say the average. And here, let's take the average value. And instead of total, that'll now be the average. The average of x times y is exactly 0.5. Right? Some of the samples have a value of 1, some of them have a value of 0, some of them have a value of 1/2. When you average across all of those, the average value is exactly 1/2. And so this is like the special case, right? If you multiply two cosines together, if they're at different frequencies, their average value is 0. But if they're at the same frequency, their average value is exactly 1/2. And this means that we can use this in order to extract information about which frequencies there are in any particular sound. We can do that by multiplying the original sound times the cosine at some frequency m. And if the result is 0, then we know that the original sound doesn't have frequency m inside it. If the result is 1/2, then we know that the original sound has that frequency inside it. Another way to write this is to say that if I can take the average of the product of those two things is equal to exactly 1/2. I take 1 over n times the sum of the cosine at k hertz times the cosine at m hertz. That average is equal to 1/2 if the two cosines are the same, and it's equal to 0 otherwise. Notice there's a special case. It's equal to 1/2 if the two cosines are the same, or if one of the two cosines is capital N minus the other cosine. So if k is equal to 3 and little m is 24 minus 3, then that would also give me a frequency of 1/2. That's because of aliasing. Right, yeah, that's here. The possibility that k equals n minus m, that comes from aliasing, which we discussed last time, where n minus m is exactly the same as m. All right, so that's the principle of orthogonality. That's these perpendicular lines. Now let's talk about why that's useful. Let's talk about music. A musical chord. Let's look up what an A major chord sounds like. Let's see if they have an example of that. Major chord. A major chord is a chord that contains 3 notes, and it sounds something like this. That's a C major chord. It contains the notes C, E, and G. So a major chord is a chord that has a major third and a perfect fifth. A major third is 4 half notes, and a major fifth is 7 half notes. All right, let's look up also what a minor chord is. A minor chord has, for example, A, C, and E. Or a C minor chord would be C and E flat and G. All right, let's talk about that. A major chord is a chord where you have a major third tone, which is 4 semitones above the root, and a major fifth tone, which is 7 semitones above the root. Just x is the cosine of omega naught times n, plus the cosine of g to the 4th times omega naught n, plus the cosine of g to the 7th times omega naught n, where g is 1 semitone, 2 to the 1/12. Right? So this one, cosine omega naught n, that's the root tone. Cosine of g to the 4th omega naught n, that's the major third. And cosine of g to the 7th omega naught n, that's the major fifth. So if we want to create an A major chord, we can take 440 hertz, and then we can add together the cosine of omega naught n, where omega naught is 2 pi f naught over fs. Right, so we can take the cosine of omega naught n plus the cosine of g to the 4th times omega naught n plus the cosine of g to the 7th times omega naught n. And we can add all 3 of those together and we get a major a major chord. That's the A major chord. Going back to C major, it's something like this. C major is 256 hertz is middle C, so let me choose 256 hertz for middle C, and now we should get the C major chord. There's the C major. All right. A minor chord is, um, let me change F naught here. F naught is equal to 440 to make it A minor. And omega naught will be 2 times pi times F naught over Fs. Now my major chord will be C major and my minor chord will be A minor. A minor chord is cosine of omega naught n plus cosine of g cubed omega naught n plus cosine of g seventh. So a minor third is 3 semitones, a major third is 4 semitones. Right? We have here g cubed, and here we have g to the fourth. So the minor chord, this will be an A minor. That should be the same chord as this. So that's the chord A, C, and E. Oh, this is actually with the A below middle C. So let's move this down from 440 to 220 to make it the A below middle C. There we go. That sounds more like. So there's the A minor chord. All right. Now, the question that we want to solve in today's lecture, the point of today's lecture, if you will, is to try to identify those three notes. We know that we have 220 hertz, that's omega naught. We know that we have a minor third above that, middle C, it should be around 256 hertz. And we know that we have a major seventh above that, right? And so in order to we want to try to understand what are the three notes that are present in that chord. All right, so we want to try to plot that. Let's just plot that chord. We'll take Fs over 20. We'll take 1/20th of a second, so 400 samples. And those 400 samples, we're going to just plot the minor chord for those samples. Sorry, my phone is acting up here. Very strange. All right, we're going to take that minor third and plot it. And I don't know about you, but I can't tell what sine waves are involved in this. I know that it has three cosines, but I don't know what the frequencies of those three cosines are. All that we can see is that in these 400 samples, which is about 1/20th of a second, it looks like it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe 14 periods in 1/20th of a second. So maybe 280 hertz is the tone, but it's obviously not just a single cosine. It's some combination of cosines that when they're added together, they look kind of like a single cosine at 280 hertz, but not exactly. This is much more complicated than just a single tone. And so the question that we want to solve in today's lecture is, how do we go from a signal that looks like this in the time domain to a representation that tells us it contains 220 hertz, 256 hertz, and whatever this frequency is, 300 something hertz, I guess. Let's find out what those frequencies are. And the way that we do that is using either the discrete cosine transform or the discrete Fourier transform. The discrete cosine transform is going to work because we started out with a chord that was only cosines. And because it only contains cosines, we can use the orthogonality principle the way that we've seen it so far. We can take the cosine at k hertz and multiply it by the cosine at m hertz. And the average value will be 1/2 if the original tone includes the cosine at m hertz, and it will be 0 otherwise. So what I can do is I can take that signal x of n, right? X is just that minor chord, and I can multiply it by a W matrix where W has every possible frequency in one of the rows. The first row will be 0 hertz, the second row will be 1 hertz, the next row will be 2 hertz, the next row will be 3 hertz, and so on, all the way down. Let's do this with, let's take a cosine at 4 hertz, and let's multiply it by a 24 by 24 matrix. So I'll create a 24 hertz cosine. Let me create two subplots here, actually. Let's see, let me create two subplots. And in subfig 0, I will do a stem plot of n versus x, and I'll add the title. And then in subfig 1, I'll do a stem plot of capital X, which is the matrix multiplication of this matrix W times this vector X. And that will show which of the frequencies. Let's add X label and Y label too. Let's add the X label. We'll say that that's time in samples, which is little n. And sub figure 1 set Y label, let's say that that's the signal X of n. And then subfigure 1, let's say that the title, and I'm going to make this a bigger plot too. Let's make it 8 samples high. We'll set the title to be the spectrum X of k as function of frequency k. And subfig 1, we'll set the X label to be frequency k, and that's the number of periods per 24 samples. And then subfigure 1, set Y label. Let's set the Y label to be the spectrum amplitude. Yeah, that's all the space I have. And we'd better set it to be tight layout so that we don't overlap everything. All right, let's see if I've made any errors in this code. I have made an error. What error did I make? I can't set the x-axis with stem, so let's just plot it with stem. Figure has to have tight layout, not subfig. There we go. So here's x of n as a function of time. You can see it has 4 complete periods in these 24 samples. And now we'll take that signal and we'll multiply it by a matrix W, such that the 0th row has 0 hertz, the first row has 1 hertz, the second row has 2 hertz, and so on. You can see here, W is zeros n by n, and then W of k comma n is the cosine of 2 pi times k times n over capital N. So k is the row number, n is the column number, k is the frequency measured in periods per 24 samples, and little n is the sample index. So down here you can see we have the frequency and the number of periods per 24 samples, and the spectrum lines up exactly. At exactly 4 periods per 24 samples, we have a value of 12, which is 24 halves. Let's multiply by 1 over 24. Divide by capital N. Then we see that at exactly 4 samples, we have the average value of 1/2. The orthogonality principle shows up where no other frequency has any energy other than 0. Only the frequency right at 4 hertz has a value of 1/2. Also, the frequency at 24 minus 4 at 20 hertz, that one also has a value of 1/2 because of aliasing. So this 4 hertz, this shows the actual frequency in the cosine is 4 periods per window. And this over here at 20 periods per window is caused by aliasing. This is called the discrete cosine transform. It's called the discrete cosine transform because our W matrix is composed entirely of cosines. Our W matrix right here is just the cosine of 2 pi times k little n over capital N. And we can use that in order to find out what's inside the minor chord. Let me take a very large matrix, let's say 400 samples, and let me create a zeros matrix, capital N by capital N, and let me do the same kind of W matrix, 2 pi times little k, little n over capital N, and then let me multiply that by the minor chord, and I'll divide by capital N to get an average rather than a sum. And you can see that the average is 0 at almost all frequencies. Up here we have the aliasing. Down here we have the values that are really, truly non-zero. Let's find out what those frequencies are. Let's zoom in a little bit. Let's zoom in on the samples between 0 and 50. And if we zoom in on the samples between 0 and 50, we see that we have significant values at 11 samples, at 11 cycles per 400 samples, and again at 13. So this is 11, 12, 13. And then again, we have something over here at around, this is 11, 12, 13, 14, 15, 16, something over here at around 16 cycles, but it's very small. You might think that this one in between is high in amplitude, but this one is only high in amplitude because it's close to the 11 and the 13. This one over here at 11, 12, 13, 14, 15, 16. This one over here at 16 is large, independent of these two, and then therefore that's the one that we should probably pay attention to. So now that we're doing 220 hertz, these are at 11 and 13 and 16. And so we ask, what frequencies are those? Those are at k equals 11, k equals 13, and k equals 16. We had a total of 400 samples. Capital N was 400. And remember that the frequency omega in 2 pi times little k over capital N, that's 2 pi times the frequency in cycles per second divided by f sub s in samples per second. So the frequency in hertz is k, the frequency in periods, divided by n, the total number of samples, multiplied by f sub s. In fact, we can fill this in. We can say that k is in samples divided by, k is in periods divided by n, which is in samples, multiplied by f sub s, which is in samples per second. Let's see if that worked out. Nope, it didn't like my text RM. I wonder if it'll like mbox. Let's try that. That's another command that sometimes works to give me non-mathematical characters. Oh. Let's see if that works. There we go. K periods per n samples multiplied by f sub s. Let's put a little times marker there. K periods per n samples multiplied by f sub s samples per second gives us f measured in periods per second, right? Cycles per second. So f is measured in hertz, which is periods per second, because the samples here cancel out. So let's do that. We have k is equal to 11, 13, 16. Let's do k as a total range between 0 and 400. And let's find f, the frequency in hertz, measured between 0 and fs. And let's plot those three samples. Set the x limit between 0 and 750, let's say. 0 and 500 maybe. Let's see, if I plot between 0 and 500, I get that the frequencies are, here's one at 220, here's one at around 260, here's one at around 320. Let's zoom in a little bit more closely and find out exactly what those frequencies are. Zooming in a little bit more closely, we see that we have energy at 220 hertz exactly, at 260 hertz almost exactly, and at 320 hertz. All right, so the tones in the A minor chord where F is equal to 220, C is equal to 260, this, and F is equal to 320, which is the major fifth, the E note. The the 260 and the 320 are just the samples that we have available. They don't line up very well with the true values of the tone. If we want to find the true frequencies, we probably need more samples to look at. Let me actually increase this a lot. Let's increase this to 4,000 samples and see if that gives us a lot more information. Let's see if we can actually run that product. Oh goodness, that's taking too long to run. Let me try 1,000 samples and see if that will run. There we go. That's much better information. Now we can zoom in and see that there's a lot of information there. I wonder if that's enough information. Let's find out. Let's zoom into the first 300 samples and see if that's enough. There's the first 300 samples. And it still doesn't look like it's giving me a lot of information about the E note, does it? Did I really add the E note? Sounds like it's there. All right. Doesn't look like it's giving me a lot of information about that. Well, let's zoom in anyway and find out, see if we can find it. There it is. We have 200. Now it's not showing anything at 220, but it is showing at 260. That's weird. This spectral analysis is a little bit tricky, isn't it? Let's try 1,100 samples just to be. There we go. Now we're getting three complete peaks. All right, let's show those three complete peaks zoomed in. There are those three peaks. And let's zoom in again and show them converted from K into hertz. Now we have one at 219 hertz, one at 260 hertz, and one at 330 hertz, roughly. There we go. So that's roughly the root A tone, the major third C, and the major fifth E. That's the same tone that we heard from that, that we heard from Wikipedia. So we need to make sure that we have enough samples and frequency. But if we have enough samples and frequency, we can get those tones back. And now here's the trick. All of that worked only because we had cosines. If we tried to multiply it by sines, all of that wouldn't work. So let me create a sine, which is, let me go from 220 hertz again, and let me do it with sine waves instead of cosines. Let me take the sine of omega naught and the sine of g cubed omega naught and the sine of g to the seventh omega naught and play those. And of course, humans can't hear phase. And so to you and me, this sounds exactly the same as this. Those sound exactly the same to you and I. If we plot them, they will look a little bit different. Let's go ahead and plot them. Um, let's plot, this will be the minor chord. We'll plot it for the first 4,000. Let's plot it for just the first 400. And then let's plot the sine minor chord. as a function of time in samples. And let's see, those should look a little bit different. And indeed, those look a little bit different. Here's the minor chord, it starts out high. Here's the sine minor chord, it doesn't start out high. You can see they look qualitatively similar, but they're a little bit different in terms of their time alignment, right? That time alignment is because the top one is constructed from cosines, the bottom one is constructed from sines. So they look pretty similar, they sound identical, but what's interesting is when we take our 1100 sample W matrix constructed using cosines and multiply it times the sine minor chord, we will get nothing at all. So here's the cosines and the sines detected by the cosine minor chord. This is not showing what I want it to show. We want this to be between, what are the frequencies up here? 200 and 350. All right, so the red one is showing the sine minor chord, the blue one is showing the cosine minor chord, and you can see that, well, they're both picking out the A root note, but the C note is only being picked out by the cosine and not by the sine. Meanwhile, the E note is being picked out by both of them. So they're both picking out the A and the E, but the C is not being picked out very well for the sine. And the reason is that when we multiply a sine times a cosine, it doesn't work, right? The middle tone is only being detected if it's in a cosine alignment. It's not being detected if it's in the sine wave alignment. And the way that we can solve that is by multiplying times a sine wave instead. If we multiply times a sine wave, let's create a W matrix, which is the sine of 2 pi kn over capital N. And let's plot that between 200 and 350. And we see that the result of that plot detects both the cosine and the sine, but with negative polarity. Right? The cosine is being detected with the wrong identity. And the sine wave is being detected here at the middle C note, but the cosine is now not being detected at all. So we've got these two problems. Number one is that whether you detect a note or not depends on whether it's a cosine or a sine. And the other is depending on whether it's a cosine or a sine, you might detect either a positive version of that note or a negative version of that note. And so the way that we solve this problem is something called the discrete Fourier transform. The discrete Fourier transform is just the same as the discrete cosine transform, except instead of multiplying by a cosine, we'll multiply by both a cosine and a sine wave, both at the same time. And we do that using the trick of complex numbers. We'll use j, which is the square root of -1, which is the imaginary number. And we'll say that w of k comma n is a complex number. It has a real part, which is the cosine at k hertz, and it has an imaginary part, which is the sine at k hertz. And so when I multiply capital X as the W matrix times little x, I get an x of k, which is n over 2 if x of n has a cosine at that frequency. And it's imaginary n over 2 if x has a sine at that frequency. And I can get that back again using NumPy absolute. So I can take this W matrix as the cosine of 2 pi little k little n over capital N minus j times the sine of little k times little n over capital N. I can multiply that matrix times the minor chord or the major chord, either one. And in either case, what I want to do is I want to take the absolute value of the result. And taking that absolute value will get rid of the difference between minus and plus, and it will also get rid of the difference between real and imaginary. And so what I get back again, oh, this is going to give me 350 to 750 is not what I want. I want just 200 to 350. And now you can see that regardless of whether I detect it using the cos the minor chord constructed using cosines or the minor chord constructed using sines, they both have energy at 220 hertz for the root A tone, and at 260 hertz for middle C, and again at 330 hertz for the E above middle C. So in both of these two minor chords, we're detecting these three notes on the piano. These three notes that are shown here, A, C, and E, we can detect all three of those notes by multiplying by a capital W matrix, where capital W is the cosine of 2 pi k n over j sine plus minus where the capital W matrix includes both the cosine and the sine. So this is um, this is basically the homework. Let's look at the homework. The homework has three parts. First of all, construct a major chord. So um, the first part of the homework is to me. There's my notepad. Here we go. The first part of the homework is the homework has three functions: DFT matrix, major chord, and spectral analysis. The first one, we want to generate a major chord at a particular sampling rate. So let's look at that. We wanted to generate a 1/2 second major chord based at frequency f with a sampling frequency of f sub s. So let's see. This is where we have omega naught is equal to 2 times pi times f over fs. And the n's are the numpy a range from 0 up to 1/2 second. 1/2 second means we want fs over 2 samples. And then we want the root chord is the cosine of 2 times pi times, oh, we've already got omega naught there, so just omega naught times n. And the major third is equal to the cosine of g to the fourth times omega naught times n. And the major fifth is the cosine of g to the seventh times omega naught times n, where g is the scaling thing that we need in order to get one semitone up. So that will be 1 octave to the 1/12th power. So we have G is 1 octave to the 1/12th power. We take that to the 4th power times omega naught to get the major third, that to the 7th power times omega naught to get the major fifth, and then we'll add them all together. Not root chord, but root note, just root, let's call it. Root plus major third plus major fifth. We add them all together and return that. That should give us, let's see, we've got omega naught is 2 pi f over fs. The n-axis goes from 0 to 1/2 second. G, the scaling factor that scales semitones, is 2 to the 1/12th power. The root tone is the cosine of omega naught n. The major third is the cosine of g to the fourth times omega naught n. The major fifth is the cosine of g to the seventh times omega naught n. If we reload homework 7, we should be able to generate a major fifth. Omega 0 is not defined. Oh, here. Omega naught. There we go. There's our 1/2 second A major. That's a C major. We could bring it down to an A major by changing the root frequency to 220. There we go. There's 1/2 second A major chord. All right. The second function is the DFT matrix. We want to create a matrix W whose knth element is j times the sine of 2 pi kn. That's already almost given to us. We want to create a W matrix, which is zeros of n by n, and we want to make sure that it's complex. And for that, we need to type d type equals complex, I think. Let's go back and check and see what I did last time. W d type equals complex. There we go. We need to specify that it's complex valued. And now we need for k, how did I do this? For k in range n. For k in range n, for n in range n, we want to say w of k comma n is equal to the cosine of 2 pi kn minus n minus j times the sine. And j is 1j, I think. How did I write that over here? I wrote that as j. Oh, I wrote j is equal to 0 plus 1j. 1j, fine. So it's 1j times the sine of 2 pi little k little n over capital N. And then let's return w. So we're just creating a DFT matrix that has the cosine in the real part of every row and column, and the sine in the imaginary part of every real row and column. Let me go back down to the homework and test it out. Here's the help file, and here's where we should generate, we generate a signal that has a cosine at 3 hertz, 3 samples. And if we create a DFT matrix, then we should be able to recover that cosine exactly. And there we've recovered it exactly. If it's a cosine, then it has a frequency of exactly 3 hertz. I've done this in 2 different ways, by the way. I've multiplied W times X, and I've also done it using the FFT. And from now on, mostly we will use the FFT. Let's look up FFT, NumPy FFT. NumPy FFT computes exactly the W matrix times the x-axis. And so it computes exactly the output. Well, I could just show you here. The output, if I take numpy.fft.fft of x, it computes exactly the same thing as my DFT matrix multiplied times little x. And so for our third task, we want to find the three frequencies that exist inside some signal, little x. Up here, for example, I've created little x as a minor chord with a, here, let's create, let's do the minor chord. Let's take find the 3 frequencies that exist inside of a minor chord. All right. So what does spectral analysis do? We want to find the 3 loudest frequencies in X, where X is a waveform and F sub S is its sampling frequency. And so to do that, we want to, first of all, we can either use NumPy FFT, or we can use our DFT matrix function. Let's use our DFT matrix function. Let's first of all say capital N is equal to the length of X, and then we'll create a DFT matrix with a length of capital N. And then let's multiply capital W times X. And then let's take its absolute value. And then let's see. Let's say first frequency is equal to np.argmax of X. And I just want X through capital N over 2 because anything after that will be aliased, right? So I want to take that argmax and I want to multiply it by what did I have to multiply to get back to sampling frequency? I had to multiply by little k over capital N times Fs. So argmax times argmax is little k times Fs over capital N. There we go. And then after I've found the first frequency, I want to set that sample to 0. Oh, let's find K1. Actually, I want to set that sample to 0 before I convert it. So let's just say x of K1 is equal to 0. And then let's find K2, which is the argmax of what's left over. And let's set K2 equal to 0. And then let's find K3, which is the argmax of what's left over. And now I want to sort those. So we'll take we'll take the frequencies will be sorted. Let's look up, yeah, let's see, how do we sort an array in Python? Sorting techniques. We can take just an array and then we can sort it and it becomes sorted. All right. That's sorted is the name of the function. So let's sort it. Frequencies is equal to sorted K1, K2, K3. And once we've sorted them, then I want to convert them into Hertz by multiplying by Fs over N. And then what I want to return is the first frequency, the second frequency, and the third frequency. I think it'll work. Let's find out. The three frequencies of an A major chord are F1, and this will no longer be an A major, this will be an A minor chord because I'm sending in the minor chord. It's multiplying by an 8,000 by 8,000 sample matrix. That could be somewhat large. This is going to be a lot faster if we do it with the FFT instead. So let's use the fast Fourier transform instead of this W matrix. Let me instead say x is equal to the absolute value of the FFT of small x. The FFT has the advantage of being much faster than multiplying by the W matrix. So let's see if it's fast enough to be able to do this in a reasonable amount of time. Line 60. What's line 60? K1 equals argmax capital X up to N over 2. Oh, it has to be an integer. Let's see if that solved that problem. Now line 65 has a problem. What's line 65? frequencies equals sorted K1, K2, K3 times Fs over n. Because I'm multiplying an array times a constant. So let's turn it into, let's say, K times Fs over n, or K in sorted K1, K2, K3. There we go. Now I'll return each of those values, K1, K2, and K3 in order, and multiply each one of them by Fs over n. Let's see if that solves that problem. Now I've got a typo. Frequencies. There we go. Let's see if that solves the problem. There we go. The three frequencies of an A minor chord are 220, 260, and 329. All right, that took some doing. We had a couple of typos in there and a couple of bugs, but once we started using the FFT, it was fast enough to be worth doing. And then we just have to do the argmax of 0 up to n over 2, and then zero it out. And then do the argmax again of 0 up to n over 2, and then zero it out. And then do the argmax of 0 up to n over 2 again, and then zero it out. All right, let's grade it and see if the grading code works. We run the grading code and we find, lowest spectral frequency is 440, not 440. Five hundred and forty point zero is not equal to 540.36. That's a pretty small error. That doesn't look like an error that's worth worrying about. All right, so if you get this error that 554 is not equal to 554.4, don't worry about it. Go ahead and check in your code anyway. Let me go ahead and run GitHub Desktop in order to check in my code. I've completed homework 7, so let's type homework 7, commit three files and push to origin. All right, looks like I have more to fix, so let's go ahead and fix the additional stuff. Commit one file and push to origin. Now let me go to GitHub and make sure that in my student code, homework 7 has the changes listed. And there, indeed, we have the changes listed for the major chord, for the DFT matrix, and for spectral analysis. So we can copy this and then go to the canvas. And if you look up the course Speech Understanding, and if it will take us to the course, then we should be able to copy the GitHub repository, GitHub URL into the homework. It's not connecting me to the course for some reason. Well, that's strange. Oh, there we go. Homework 7. There we go. Go ahead to homework 7 and enter your um, enter the URL of your GitHub and then go ahead and submit, and you should be able to submit in that way. All right. Yes, you should be able to submit like that. Oops, something went wrong. Please reload the page. Okay. Well, maybe it's something went wrong because I'm a teacher, not a student. I don't know. Anyway, that's all for today. So please go ahead and do the homework, and I will grade it once you've submitted it. Let me stop recording, but start sharing. Here we go.